With that, we will move on to the next talk by Joris Witstok, who is a student at Cambridge, and he will be telling us about uncovering physics of star formation in the EOR with C2 and O3.
Yeah.
Take it away.
Thank you very much, and my name is Joris Witstok. I'm a third-year PhD at the Kavli Institute in Cambridge. Today I'll be talking about looking at C2, as Sander has just nicely introduced for me with ALMA, but also the O3 line at 88 micron. So very briefly, we've all seen this overview many times now, and I'd just like to point out again, so before James Webb, of course, the rest frame optical were really limited to the lower redshifts. And then even if you go to the rest frame UV, where we have, of course, the brightest line being Lyman alpha, this starts being absorbed at redshifts of about 6 or 7. But already with ALMA, we can perform these spectroscopic studies at high redshift, well into the Epoch of Reionization, using the mainly C2 and O3 lines above redshifts of about 4 and 6. And what's more, if you use ALMA, you actually get spatially resolved spectroscopy. So you can make these beautiful velocity maps, for example. So the sample I'll be talking about today consists of 4 galaxies. And so rather than being spectroscopically confirmed with Lyman alpha, as Sander has just explained, these have been confirmed with C2 using ALMA. And so what are these systems like? Well, they're quite UV bright. They're normal star-forming galaxies, so star formation rates between about 20 to 60, and stellar masses of between 1 to 4 times 10 to the 9 solar masses. And you can see 2 of the SEDs on the right here. So I'd just like to briefly mention, again, the selection technique involved using the medium to high equivalent widths in the optical, rest frame optical, to allow the Spitzer photometry to really get a narrow constraint on the photometric redshift before scanning with ALMA. So then on top of the ALMA data, we also obtained Hubble rest frame UV imaging for 2 out of the 4 sources. And so what can we start to see? Well, I'm showing the O3 contours here on top of the rest frame UV. And you can see the O3 line traces the rest frame UV quite well, but there's not a perfect one-to-one match. And this is the same in the other 2 sources. And then finally, so in our sample, we also simultaneously get a detection on, or a constraint on the dust continuum at 90 microns. And so we don't actually detect any dust for any of the 4 sources, but this does give us some really interesting constraints. And I'll talk about that at the end of the presentation a little bit. So, so with this sample then, we have 2 traces of the ISM. And so first of all, the existing C2 data traces the neutral part of the ISM, while oxygen 3 is only really produced in more highly ionized gas. And so, as Sander already mentioned, what we can look at then is, for example, the line ratio. So oxygen 3 over C2, I'm showing you here in 2 of the sources. So for example, in this source, we can already see across the source, the ratio changes from this gray region where we see ratios of about unity all the way up to ratios of about 10 and even higher. And we can resolve this to the beam size, which corresponds to roughly 2 kiloparsecs at this redshift. But at the same time, we also see for other sources, for example, this one, just a generally quite low ratio of somewhere between 3 and 4 for this particular source. So we can start to compare our measurements with some reference samples then. So here I'm showing you the line ratio as a function of star formation rate. And well, two main reference samples that we have at low redshift are the dwarf galaxy survey, which consists of metal poor dwarf galaxies, and then as well a sample of local ULERGs. And then the high redshift galaxies are the colored points in the top right here. And so these all occupy a slightly different space of this plot. So we can start to wonder, are their ISM properties actually systematically different? But so one thing we found is if you look at the same ratio, but now as a function of the equivalent width in the optical, so oxygen 3 and H beta, we see this general trend both in the dwarf galaxy sample as well as our high redshift sources. And so we even see that if you just take this subsample of dwarfs at higher equivalent widths, there doesn't seem to be any obvious difference. And secondly, if we use a simple nebular model, we can see that we can reproduce the values we see for our systems with a young, so about 1 mega-year burst of star formation, and a sort of moderate ionization parameter between about -3.5 and -3. And finally, we're currently still working on trying to see if we can, for example, explain some of the spatially varying line ratios that we see in our sources. So just the last part I'd like to spend on what we could say about the dust with our measurements. And so as we've already heard from Rebecca, dust is really a key ingredient in galaxy evolution. And so it helps in forming molecular gas, but of course also it crucially obscures star formation in the UV and optical. So what can we learn by looking at dust at high redshift? Well, first of all, I think what's really interesting is just because these systems are, we see them at a time when the universe was so young, they simply haven't had a lot of time to actually form their dust. And so we can start to compare the amount of dust we see to what is theoretically expected from models, for example. And secondly, what we also expect to see, which we've already heard about, is higher dust temperatures. So this is just comes down to higher specific star formation rates, where if you have more massive stars heating up their surrounding dust, then the hot dust becomes this more dominant component of the whole system. So what do we actually see? Well, we, of course, then have two constraints on the dust continuum, both coming from the existing C2 data and then our new upper limit at the 90 micron regime. And so I would just want to highlight this specific source. You can see our non-detection combined with a very significant detection at longer wavelengths, we can actually rule out a lot of the higher temperature dust templates. And so for this specific source, we see that peak temperature must be somewhere below 40 kelvins. So if we start to compare that to other measurements in the literature, this kind of fits in. So as you can see from lower redshift, we do see this general trend of higher dust temperatures towards the higher redshift. And so this is the measurement I was just showing you. And we do see this is just about in mild tension with some of the even more conservative trends we might expect. But I think the only thing we can really conclusively say about this is that there's just no clear picture at high redshift yet. And that's just mostly comes down to, most of these systems only having at most 2 or 3 photometric data points. And so as Sander already pointed out, we just need more measurements. So just one final point then, this low dust temperature in the system actually then requires a significantly, relatively quite high dust mass. And combined with the also relatively low stellar mass, we then can convert this into a dust yield. So how much dust mass is produced per dust producing star, which results in this number of up to about 4 solar masses. And this is tentatively higher than where you would expect the maximum yield to be from AGB stars and supernovae. And so this might be, for example, the evidence for growth of dust grains in the ISM, which is quite exciting. And that brings me to my conclusions. So presented 4 new detections of the oxygen 388 micron line in normal star-forming galaxies at redshift 7. We find a tentative trend with the equivalent widths of optical lines, and finally we see quite surprisingly low dust temperatures, which may hint at dust formation by grain growth. So thank you very much, and yeah, looking forward to seeing any questions.
Thank you so much, Joris, for a great talk. We'll give people a little time to enter questions in the Slack.
Okay, here's the first one already from Sarah Bosman. Do you see any velocity offsets between C plus and O3 submitter lines?
Yeah, that's a good question. Not any major velocity offsets. So I've got all the spectra here, red being the O3 line and blue being the C2 line. So for example, in this source, you see a slight velocity offset, but mostly they generally agree quite well.
So while we wait for, oh, okay, here's the second question from Rebecca. What is the resolution of your C2 and O3 data? Is there any way you could be resolving out extended emission?
Yeah, that's also a great question. The whole measurement set is quite heterogeneous. So for these 2 sources, we've got slightly lower O3 resolution, but slightly higher C2 resolution. But we do also have the initial low resolution C2. And then for these sources, we have slightly higher O3 resolution, which may resolve out some of the emission. But yeah, there's not a lot of evidence for that because we do see it's quite clustered on top of the rest from UV.
So we have another question. Are there any AGN signatures in your sources, and do you have rest frame UV spectra?
That's also a very good question. I would have to double check. Not that I know of, but let me get back to you on that. Yeah. Okay, great.
Yeah, feel free to answer it in the Slack later. And I just have a really quick question on your SED. Fits to the interesting result that you're finding lower dust temperatures. I saw that you have some emissivity spectral indices that are pretty low, like as low as 1 in some instances. Could you speak about the choice of beta IR there?
So what I actually do here is I just take templates from any temperature and then allow the beta to vary between 1 and 2.5, and then the non-transparent models are actually just the values that are allowed within the limits. So say for this temperature, it's barely allowed, but only if you take this very low beta value, if that makes sense.
Right, yeah. But yes, then the flux could be lower, of course. yeah, cool, great. Well, it's time to transition now. So thank Joris again, and pepper him with questions in the Slack.